Hello everyone, welcome. And today we'll be deriving the formula for the sum of squares. And as you can see, the sum of squares is n cubed upon 3 plus n squared upon 2 plus n upon 6. So we'll be deriving this formula from sequence. But the first thing I want you to know is okay, before we get into it, please subscribe, like. It will really mean a lot to me if you subscribe and like. So let's get into it. And already there are videos on YouTube on how to derive the sum of squares, but for me it was a little bit abstract, since that it was taken from not from the sequence, it was taken from a different relation and then combined to form the sum of squares. Though it's nothing wrong with that, but I wanted to use the actual sequence and derive the formula for the sum of squares. So but before we get into it, I want you to first note that when it comes to deriving formulas for sequence, especially sequence and series, it is mainly by observation, mainly by observing the sequence, that you derive these formulas, whether it's sum or the nth term. It's basically by observing and deriving these formulas. So for example, if you take for example the sequence 5, 10, 15, 20, you can easily see that this is an arithmetic progression of 5, where you add subsequent amount of 5 to the previous term to get the next term, and so it will have a formula, the arithmetic progression formula. And this formula is also derived by observing that you only need to add to the first term the number of times that the 5 or the common difference has been added, so which will be n minus 1, to get the n term. So by observation you have this, not just by magical presumption. They basically observe this sequence and then get these formulas out of it. And if you can see, for example, in the geometric progression here, you have 2, 4, 8, 16. You can easily see that this is being multiplied by 2 times 2, 4 times 2, 8 times 2, 16. So this is a geometric progression with the formula like this. So basically I didn't just assume that this was multiplied by 2. I had to observe, and then so basically my point I want to stress is that you have to really observe this sequence to have a logic on how the sequence is working to derive the formula. For example, take this sequence for example. Because you have to observe, it can be very difficult to derive the formula for sequence and series, because you don't know what changes is being made to the series, and so you have to do trial and error to get these particular formulas. For example, take 8, 14, 24 and 38, and if they ask you to derive the formula, the n term for this series, the formula for the n term, it will be very difficult because you have to do trial and error. So in this case you have to factorize 2, which you get by doing trial and error. Okay, let me try 4. Okay, 4 does not, until you get to 2, and then it's okay, I have to factorize by 2, and then after factorizing by 2, okay, I can dissociate these terms into 1 plus 3, 4 plus 3, 12 becomes 9 plus 3, like that. And then basically you see that this term is progressing as a sum of squares. This is 1 square, this is 2 square, this is 3 square. So okay, this is n square plus 3 multiplied by 2 is the n term. So you get this by doing trial. It's nothing easy. You have to do lots of trial and errors to get these formulas that we appreciate today. So we similar for the sum, for deriving the sum. Take for example in the arithmetic progression, to derive the sum you basically need to take the progression, and then take the starting from the first term going upwards, and then take the progression starting from the nth term going downwards. And then what you observe is when you add these two terms together, you basically get a constant term being recurrent, which is 2a plus n minus 1d. So each of these will become 2a plus n minus 1d. I don't want to go into these. So basically when you sum these two together, this also is a sin. When you sum these two together, You have 2 Sn equals 2, and then you divide and get the answer. So same for this likewise. You basically observe and say, oh, in this case, if I multiply this and then I subtract, I'll end up having these constant terms being recurrent. And so basically so it's all about observing. So for in this case, after deriving the formula, if you have a progression 1 2 3 4 with a common difference of 1, then Sn after substituting becomes n square upon 2 plus n upon 2. Please take note of this. Sn is equal to n square upon 2 for a progression of 1 2 3 4. We'll be using it later. And then also for a progression of 1 3 5 7, then substituting in that Sn formula, but this one will be calling it Sx. So you will end up having n square substituting, because the common difference is 2, first time is 1, and you end up these two terms will be using it later, so please take note of it. So basically the point I want to stress, it's basically by observation that you get these formulas. So now let's get into the derivation of this sequence, this series. So the point I want to I have already stressed the point that it's by observation that you get these formulas, not by just developing them out of thin air. Trial and errors. So for the point for deriving the formula of the sum of squares, the point you have to observe is that the product of the differences and the n terms sums to Sn square. It sums to the sum of squares. What I mean by this, let me show you. So this is the progression 1 4 9 16. If you take the difference between successive terms, so 1 minus 0 is 1, 4 minus 1 3, 9 minus 4 5, 16 minus 9 7, right? If you take these differences and you multiply them by the successive n terms, you will end up having the same as the sum of squares. So for example, let's assume that n was 3, so the sum of squares will be 1 4 and 9 summing up to 14. If we take the differences, which is 1 3 5, 1 times n, it becomes 1 times 3 in the case of n equals to 3 3 times n minus 1, 3 times 2 becomes 6, 5 times like that, you'll see that it also sums up to 14. So the sum of the product of the differences and the successive n terms gives Sn square, gives the sum of squares. So this observation is very key to deriving the formula. If you have this observation, then it becomes very simple to derive the formula. The product of the differences sums up to n square, to Sn square. So you can also see for n equals to 4. So if n equals to 4, then we also have to add 16 to this. It becomes 30. And then 1 3 5 7, it's progressing by 2, so 1 plus 2 3. So 1 times n, so 4 in this case becomes 4. 3 times 3 in this case, n minus 1 is 4 minus 1 3, so it becomes 3 times 3 9. 5 times n minus 2, in this case 5 minus 2, it becomes 4 minus 2, it becomes 2. 2 times 5 10. You see that it also sums up to 30. So the sum of the if you have that concept, then it becomes easy to derive the formula. So the sum of the product of the difference and the n term sums up to n square, so Sn square. So now let's get into it. So we can see this mathematically by taking the differences. So as we've seen before, t1 minus t0, so that is 1 minus 0 times n, 4 minus 1, which is t2 minus t1, times n minus 1, which is 3 times n minus 1. And we can see this mathematically happening. If we sum this up, you can see that this gives n times t1 is n t1, n times t2, n t2, like that, going downwards. You will see that these terms successively cancel. Of course, T0, I've added it. T0 is 0 basically. I've added T0, but there is no time after 1. So this is 0. This will cancel this. This will cancel this. So the only thing that will remain in the ending will be NTN, because everything will cancel. This will always cancel this, such that only this one will remain NTN on this part. And similarly, expanding this, you have minus T2 plus T1, like that, going downwards. You see that this successively cancels this, so only remains T1 here. It will cancel 1 out. So T2, only 1 T2 remains here. Here this 2 will cancel 2 out, so only 1 T3 remains. So you see that you have T1 plus T2 plus T3. So this will basically be the sum of squares on this part. So carrying all out the, so this will cancel this going this way, and then in the end you'll have the sum of squares here, and then this, remember at this point you have NTN here, and at this point it will sum up to n minus tn. Expanding it, you have n minus tn minus n minus tn gives you 0, which leaves tn here. So the basic points we have to stress and get in mind, both mathematically and observationally, is that the sum of the differences and the n terms ends up giving you a sum up to square. So if we call the sum of the differences and the n term sy, then sy will end up being equal to sn square. So let's get that straight. So with that, let's move on forward. So now we already know that T1 minus T0 is 1, T2, I've seen it before, 3, it's progressing by 2, T2 minus T is 3, T3 minus T2 is 5, T4 minus T3 is 7, like that. And then we can therefore substitute the actual values and see what we get. So in the first case, it will be 1 times n, 3 times n minus 1, 5 times n minus 2, and 7 times n minus, like that. And so if you look here, we can factor out n out, and then we'll see we have a simple linear progression which we spoke about earlier, and I told you to remember. So we called that earlier Sx, and we have found the value for it. So this is a simple linear progression of which we can calculate the sum of n for it. So on this side, on expanding this, you end up having minus 3. On expanding with this one, you end up having minus 10. On expanding this, minus 21. Now what you will notice about this progression is that you can separate this into 2. Minus 2 minus 1. This becomes minus 8 minus 2 minus 18 minus 3. So you can separate it into 2. And what you'll find out is this is basically the sum of n Sn. It's basically a progression of 1, 2, 3, 4, which we found previously. And then what you'll find out is if you factor out 2 from this one, you end up having the sum of squares, 1, 4, 9. So with this, the only thing you should take note of is that because this sum of squares 1, 4, 9 starts at this point, it has already skipped one term. It will not sum up to full sum of squares. It will not sum up to the actual sum of squares. It will, the last term, which is n square, will not be present. So we can write a relation, assuming now, taking now, this is the sum of the difference and the product, which is sy, we said before. This should be equals to, according to this, n into minus 2 into this. This we found earlier as a 6. This we know is the sum of squares, and this we know is Sn. So we can basically write a relation. Sy we know is Sn square, and then this is minus 2 into, this is Sn square but less the last term, since the last term will not be present in this sequence due to the position it starts. Similar to this is the sum of n, but because it starts one step less than n, it will be a sum of n term but less that last term. So with that, we can expand, and then we substitute the initial values we had for each of these things. Sn, the initial value we had for Sn, we'll substitute it and expand the bracket. And then after that, this is basically math. We can collect Sn square over, so it becomes 2 Sn square plus Sn, which makes 3. And then you can run through this, so this is n square, and then it becomes n cube. N times n square becomes n cube. We've carried that over there, and then we've expanded this one, and then this becomes 2n square, and then this substituted for it as n square upon 2 plus n upon 2 Sn plus n. So we expand this bracket, this becomes 2n square minus n square upon 2, which summates to 3n square upon 2, and then subtract minus n upon 2 plus n, and then it ends up being n upon 2. Now 3n square is equal to this, divide throughout by 3, and we end up with the formula, which is the formula for Sn square, which is n cube upon 3 plus n square upon 2 plus n upon 6. So this is proved basically. So this is how you go about proving it. Thank you.